My name is Jess Baker. I did my lab on the motion of falling objects, and I'm in section M01. So my main objectives were to compare the velocity of two different objects in freefall, explore the effects of air resistance on falling objects, and try to find terminal velocity. I did this by observing the motion of two objects, one that drops rapidly and one that drops slowly. My object that drops rapidly is a water bottle. It starts at frame 47 and ends at frame 52. It's 1.05 seconds, and I used Tracker to find the distance between each interval, and I used a calibration stick on the water bottle. And then I did the same thing with the paper towel, although it kind of floated around a little bit, but it still worked. And the start frame was 51 and the end frame was 65, which ended up being 0.99 seconds. And I used the origin as where the paper towel started. So then I wrote a code to model the data. The ball position and ball velocity both started at 0. And then the time step was 0.01 so that I could gather as much data as I could. I used the force of gravity as the only force on the object, since that's all we considered for the beginning of this lab. The force of gravity was just m, which is 9.81 times the mass of the ball. And then we used the momentum principle to find the velocity of the ball, which is the ball velocity plus F net over the mass of the ball times delta t, and then use the position update formula to find the new positions, which was the position plus the ball velocity times delta t. And then when I ran it, it looked like this. As you can see, it starts out slow and then drops very quickly, which is what the water bottle did. And then I plotted the data from the output of the program. And as you can see, this is my data and this is my computer model. The model does not consider drag, but this does, and so we'll use a new model to put the drag so that they fit together better. And then I used the same code for the paper towel. All I had to do was change the mass, and the paper towel ran like this. Similar, but it was a little slower because it didn't weigh as much. And then I compared the data here too, and as you can see, the paper towel in real life didn't really increase in velocity at all. It almost began at the terminal velocity. You can, even though it's position versus time, you can tell the velocity by the slope of the line. The slope stays the same, therefore the velocity is staying the same. Yet the model in the green predicted that it would, the velocity would keep increasing, which is not what happened. So we must find a better fit for this model. So what does this mean? So here we added the drag force, and then the line really flattened out, and this happens because the drag force is proportional to the velocity. So it keeps increasing, and the net force will eventually equal 0 as once the forces equal each other, so the pushes and pulls will counteract each other, and the velocity will stay the same, as said by Newton's second law, that an object in motion will stay in motion unless a force is acting on it. So what if? What if I kind of started off throwing the ball down rather than just dropping it? By changing the initial velocity to -5 in the y direction, the model with drag hits the terminal velocity quicker, but the model without drag just keeps increasing the velocity, as shown by these graphs. The velocity is the slope of the position line, so when the line is curved, the velocity is changing. So as you can see, when there is drag and it starts out fast, it hits its terminal velocity quicker since the velocity is fast, so there's bigger drag force on it. So the chief results were that the drag force is opposite to the force of gravity in free fall, causing pushes and pulls to equal 0 and instilling terminal velocity by Newton's second law. Thank you.